So good afternoon, students. Our plan for today is to finish topic 2 until just before the intermediate value theorem, which means that evaluating limits will be completed today, along with checking of continuity. And then subsequently we'll move to finish up the tutorial questions, okay, to continuity. Then after that, we will leave the intermediate value theorem to the next week, okay, so that you have some time to digest the concept of continuity and the procedure, right, of inspecting the continuity of a function. So that's the plan for today, which is also the case for the earlier class. Okay, so actually we have covered quite a bit of the limit evaluation techniques already. Okay, so you do see that direct substitution is the one that you should always try first. Okay, because this guy is going to tell you a lot of things. Right? If only you get the indeterminate form, then you try the rest. If you do not get an indeterminate form, which means that you get a value or infinity or 0 or whatever, no indeterminate form, then that is the limit itself. So there's nothing else to do. Okay? So you should always try the easiest method first, which is direct substitution. Can okay? But certainly, direct substitution will only work for continuous functions, as you'll see why later on. Right? So hence, once again, you'll be, of course, tested on the rest of the methods covered. Okay? This last L'Hopital's rule will not be covering in this topic 2 because it requires derivatives, that means performing differentiation, right, which we have not covered yet. So we're going to cover that at a later topic, okay, after topic 3. So now let's go back to where we stopped at, and that is the squeeze theorem. So just a quick recap, and that is squeeze theorem actually very so-called, graphically easy to understand. Because you're just looking for two functions, right? An upper bound function with a lower bound function, which the two functions are going to so-called bound your f of x. So the f of x is the function that you want to evaluate the limit for. Okay, so you're looking for some upper bound, lower bound function that is going to squeeze f of x. So therefore, in that sense, right, you take the bound of f of x and then try to manipulate into this form, into exactly the function form, and then you can recognize what is your lower bound and your upper bound. Then subsequently, you just find the limit of the lower and upper bound. Hopefully, they are the same. And then by the squeeze theorem, you can say that the limit is actually the same as the upper and lower bound functions. Okay, so that's the concept here, because you are really trying to go towards this common point for all functions. So that's the squeeze theorem. And we have gone through this exercise already. Okay, so now we're going to use the squeeze theorem to find the limits of these two expressions here. Okay, why the two special expressions is because this sin x over x expression, right, is a very common expression that is encountered in electronics. So if you were to plot the sin x over x expression, you get something that looks like that. Okay? Yeah, so this sin x over x function is very common in electronics and electrical signals. It's also given a special name called the sinc function, S-I-N-C. Okay, if you Google S-I-N-C, then it will state that it is representing sin x over x. Okay? So therefore, the limit of this guy as x goes to 0, if you just make an inspection on the function itself, right, you're going to get 0 over 0. Okay, so sin x over x, as x approaches 0, is going to give you an indeterminate form. Okay, 0 over 0. And you can verify that when you put your mouse, right, at x equals to 0, you see that the function value there is actually not defined. Okay, you see? Right? But then from visual inspection of the graph, we can see that it is approaching 1. It means the limit is actually 1. Okay, but yet the function value is not defined there. So hence, we'll see how we can use the squeeze theorem to define this limit. And this is also required in the derivative. Later on when we look at the derivative, that means how to differentiate sine x and cosine x, right? We will need the two expressions here as well. So this is just a demonstration of the squeeze theorem further. So how to get this limit? Really, we look at some simple geometry. So you can see here that you have this sector, right, which is comprised of a radius and an arc. Okay? So the radius is 1. And then by now, I think you should know that the opposite projection is a sine x. So that's assuming that the angle here is x. Is that right? The echo is quite a lot. Okay? So you can see that the angle here is x. So therefore, the radius is 1, right? So hence, the opposite must be 1 times sine x. Adjacent must be 1 times cosine x. Okay? Because I think by now we know that sine and cosine, they are just projection functions onto the opposite and the adjacent. So then, you also see that there's an arc length here, right? Which is labeled as x. So that's also correct because arc length, the function is s equals to r theta. So in this case, the radius is 1, Then the theta is just the angle x, Theta is the angle. So therefore, in this case, the angle is x. So therefore, 1 times x is x. So hence, the arc length here is indeed x. And then subsequently, you notice that if you have this small triangle, you just look at this small triangle in orange. Okay, this small triangle. And you compare it with the big triangle in light blue, this big triangle. So you notice that actually they are similar triangles, okay? So because of the similarity between the two triangles, right, then we know that the ratio between the opposite and the adjacent will be the same for both triangles, okay? So sine x over cosine x is the same as df over dA. So, but because this radius is 1, so if this radius is 1, right, that means if you flatten this hypotenuse down to the x-axis, then you will notice that AD is also 1. Okay? So this is also 1. This distance, right, is also 1. Okay, as you can see the label here. So which means df over AD is just df over 1. So hence, from similar triangles, right, we know that df is actually your tangent x. Yeah, in fact, that is exactly the meaning of tangent x. Okay, the meaning of a tangent x is really you extend, okay, you're going to extend this cosine x, right, to the point whereby you have the same radius and you draw a line upwards such that it intersects the projection of the radius. Then that line, the length, is given by tangent x. Okay, so that's actually the graphical meaning of tangent x, but it's not exactly a projection. Okay, it's not exactly a projection of your hypotenuse, right? So maybe not so easy to visualize, okay, unless you work out through similar triangles. Okay, but that's not the important thing. The important thing is that, right, we found out that this df is tangent x already. So then we observe something interesting, and that is, right, you see this arc length x is always longer than sine x. Then, but the arc length x, right, is going to be shorter than tangent x. Okay, so by visually inspecting, right, you can see this relationship, which is actually given here. So sine x is less than sine x is less than x, and x is less than tangent x, pertaining to the lengths. Okay, so if you are okay with that, right, then our objective is to work towards sine x over x, this expression. So the first thing to do is to divide by sine x first. Okay, because you want sine x over x, right, but you have x here. So maybe we can just divide by sine x first and then take the reciprocal. So you can see that if I divide by sine x, sine divided by sine will be just 1. Tangent divided by sine is actually 1 over cos. So then you reciprocal. Okay, so you notice that when I reciprocal, I mentioned yesterday that I have to change the sign. I have to swap the sign. Okay, because when I take reciprocal, right, then actually a big number, let's say 1, a small number 1 will become a big number. Okay, so therefore, you can expect that if I reciprocal, or rather, if I reciprocal, I switch signs, and then I switch back. So I just really have to sort the lower and upper bounds. Okay, so therefore I get this expression. So the purpose of writing this down is that you notice that actually the function that you want is now bounded already. So what are the upper bound and lower bound? Lower bound is cosine x, upper bound is 1. So therefore we can clearly just find the limits for the lower and upper bound functions. And then because they are the same, because cosine 0 is just 1, direct substitution. Then we mentioned the limit of a constant is also just the same constant. Okay? So hence, right, your limit for sine x over x is indeed 1. So this agrees with the graph that we showed earlier. Can, okay? And then there's actually another meaning here. The meaning is, if this ratio has to be 1, right, that means both functions must approach the same expression as x approaches 0, right? Because how can they be 1 if the numerator is different from the denominator? That means they must be somewhat the same. Okay? So in fact, they are. If you plot y equals to x and y equals to sine x, then you zoom into the origin, which is at x close to 0. Then you notice that as you zoom closer and closer to 0, you can visualize that, or you can see from here that, right, the two graphs are coincidental. That means sine x approaches to x. Sine x approaches to x as your x is very close to 0. Okay? So this is the reason why you get a limit of 1 here. Because sine x is going to approach x as your x approaches 0. Observe that? Okay? So therefore we have the small angle approximation formula. Sine x is approximately x when the angle x is small. Okay, and you can verify this yourself. You can press the calculator, for example. So let's say you have sine angle A. Okay, so you see when angle A is 1 radians, right, the sine of A is not so close. Not so close, right? But if let's say I put a 0.1, so if this is 0.1, you notice sine A is 0.0998. So that's about 0.1 Then if you put 0.01, even better. You see? 0.01, this is 0.0099998. So you can see it converges towards 0.01. You see? Okay? So indeed, this has to be true because of the graph shown here. Okay, so this is also telling us that the gradient of sine x at x equals to 0 is 1. Okay, because the gradient of f equals to x or y equals to x is 1 Well, it's 1 everywhere So since they are coincidental near 0, that means the gradients are the same. Is that right? Okay. So then, there's another more general result, in fact. Okay. So if you look at this expression here, I mean this graph here, right? You can imagine if you press down this hypotenuse, that means it's like you like flatten it flatten it As you flatten it, right, the triangle becomes flatter and flatter, right? Flatter and flatter. So what's going to happen is that, right, if you have a very flat triangle, you'll observe that sine x is approaching tangent x. So it is shown here. You see this very flat triangle, right? If I flatten it some more, but I mean this is flat enough. Okay, so you can see that, right? The arc length is very similar to the sine x, the opposite projection, is very similar to the tangent x length. So therefore, we can come up with the conclusion. Sine x approximately x, cosine x approximately 1. Then tangent x also approximately x. Okay? And this is true when you have x being a very small angle. Is that all right? Okay? So certainly if you plot tangent x here, right, you also notice that tangent x is also coincidental with sine x. It's also coincidental with x near 0. You see? Okay? So if it's far away, of course, not in good agreement. But as you zoom very close to the 0 here, right, you can see all the lines are coincidental already. So therefore, they are approaching the same thing, the same value. Okay, x, sine x, and tangent x. Any questions? Okay, so the important takeaway is just this sine x over x are equivalent to 1. Okay, so then what about the other limit here? So we can evaluate this limit, okay, using conjugate rationalizing, which is something that we have learned before. Okay, so you can see that from this part, right, if you try to do direct sub, as what I have recommended that you always do first, you notice you get a indeterminate form, 0 over 0. So of course, then this requires something else. Okay, so you say here that use rationalizing by conjugate multiplication. So you can see that there's only one conjugate because x has no conjugate Then this 1 minus cosine x, the conjugate will be 1 plus cosine x. So just the minus change to plus, that's all. Okay, so of course you divide by the same expression. Then you notice that this is 1 plus cosine x times 1 minus cosine x. That will give you 1 minus cosine square x. But 1 minus cosine square x is sine square x, right? Okay, then when you come to this part, right, if you were to sub in 0 into the expression here, you still get 0 over 0, quite clearly. Okay, so the trick is actually to make use of the sine x over x limit that we have found earlier on. So we split the sine square into sine times sine. Then of course, the limit just apply to the individual functions. So then this sine x over x, we already proven that the limit is 1, what? Then what is this? Direct sub, Direct sub, you get sine 0 is 0, Then 1 plus cosine 0 is 1. Okay? Cosine 0 is 1. So therefore, you really just get 0 over 2 times 1, which is 0. Okay? So you can see that 0 over 0 here can actually result in a finite limit of 0. So we'll be making use of this result in the next topic, where we derive the derivative of some trigo functions. Is that all right? Okay. So actually in the process, you notice that we make use of rationalizing, but we also make use of squeeze theorem, okay, for the first part. So therefore, this kind of demonstrates that sometimes, right, you need to apply multiple methods to evaluate the limit. Okay? Yeah, so therefore we come back to the same table here. Right, so this is a recommendation now. Okay, so we do direct sub first. If you get 0 over 0 or any indeterminate form, then you can try out the rest, dependent on how the expression looks like. Okay, so we're going to have some further examples in the tutorial questions later on. Yeah. Yeah. Is that all right? Yeah, so so therefore, recommendation table, right? You'll see how I can use this later on. Okay, but I did put a note here, and that is, right, this recommendation is a recommendation, but sometimes it may not work. Okay, sometimes it may not work. Right, and indeed, some limits are very difficult to evaluate. Okay, so much so that we probably have to rely on numerical methods like computers, okay, to assist us. Okay, but of course, for the course, you'll be just given whatever type that you see in the lecture examples as well as the tutorials. Okay, won't get out of the conventional type. So now we move on to the concept of continuity. Actually, continuity is a very straightforward concept in the sense that you just look at the graph here, right? So what do we mean by continuous? Okay, so we ask, is your function continuous at point A or not? At point x equals to A or not? And if you can draw a continuous curve or line cutting across that point x equals to A, at x equals to A, then the answer is yes, right? Because that's what continuity means, what? Okay, you have to draw across that point in one stroke. So if you can do that, then yes, the function is continuous at point A. Okay? Then of course we can ask the question, right? Is the function continuous in the entire interval C to D or not? Well, if you can draw a continuous stroke or continuous curve without lifting your pen or pencil, right, from all the way from C to D, then yes, the function is continuous in C to D. Okay? So this is a very simple, straightforward understanding, I hope. Okay, but mathematically, what does that mean? Mathematically, it really means that the limit must be equal to the function value. Okay, so you can see the limit here, right, is that we are trying to approach, let's say at x equals to a, right, x equals to a, so we're going to approach x equals to a. Right, so if you approach x equals to a, what is the function value? Approaching. So if the function is approaching its function value at that point, that means that's good as saying, right, you can draw continuously one stroke across that point. Okay? Or rather, right, you can converge to that point which is on the graph as well. So therefore, that's the mathematical definition of continuity. Just this blue box here. Okay? So every time we need to check for continuity, we will just check if is the limit equal to the function value. If it is, right, then yes, continuous. If it isn't, then no, not continuous. Simple as that. Can Okay? Any questions with the concept here? Good? Okay, so for example, right, any polynomial function is continuous everywhere. Because this equation, right, is satisfied for all x equals to a in the entire domain. Okay, so any polynomial function, you notice that, right, if I take the limit as x approach a, let's say this polynomial function, for example, is like x cubed minus 2x squared plus 1. Say cubic polynomial. So it doesn't matter what is a, right? You just substitute a inside. So you get a cubed minus 2a squared plus 1. Doesn't matter what is a. A can be 1, 0, minus 200 or whatever. You sub inside, you can calculate this, ma. So if you can calculate this and it gives you a limit L, that means it's a defined number lah. Then you notice that actually when you sub in, right, this number is the same as f of a. Because you just do direct substitution. So f of a is exactly this expression as well, ma, because you just sub x equals to a inside. So therefore you can see that the limit is equal to the function value for all a. Doesn't matter what's a. Okay? So therefore, indeed, a polynomial is continuous for its entire domain of R. Can Okay, so then maybe one can ask, well, if the function is continuous, okay, limit equals to function value, then what happens when the function is not continuous? So then we have to look at what are the types of discontinuity. Okay, so very common type, step or jump discontinuity. Okay, so that means x equals to a, right? On the left, the limit not equals to the function value or the limit on the right. You see? Left limit not equals to right limit. So therefore the limit does not exist, what? The limit as x approaches a doesn't exist. Left not equals to right limit, yesterday we mentioned. Okay? And because of that, right, how if the limit doesn't exist, how can it be equivalent to the function value? So therefore violate the mathematical definition of continuity. Okay? So this guy is like a jump discontinuity, we call that. Then secondly, there's also this infinite discontinuity. This one also very common. Like 1 over x or 1 over x squared, right? Because as x approaches a, your function go to infinity or minus infinity. So therefore you cannot possibly draw from positive infinity, come back. Okay, not possible. So therefore there's a discontinuity there as well. So we call that infinite discontinuity. And then the third type is the most interesting one. Okay, the third type is when you have an expression that you can find the limit actually. The limit is L, that means some defined number, it's not infinities. Okay, that means the limit exists, but the function value is undefined. Okay, at the same point x. So for example, right, let's say this x squared minus 1 over x minus 1. This one we have seen this guy before. Okay, So if you plot this guy, right, actually at x equals to 1 is undefined because you cannot divide by 0. However, the limit exists what? Because you can just factorize this, right, cancel off the x minus 1, so you get x plus 1, then you sub in x equals to 1, right? So you get a limit of 2. You see the limit is 2, you see, okay, limit is 2. So therefore, the limit is 2, but the function value is not defined at 2, Okay, so therefore there's a hole. There's a hole there. But yet, right, this hole can be removed by defining f of a equals to the same limit L. Okay, that's why it's called removable. Because you can fill up the hole by defining f of a equals to L to this expression. Okay? And this thing, this approach, you cannot do for this, you cannot do for this. So the two discontinuities, the jump and the infinite types, are not removable. Is that right? Okay? So this is just introducing you several types of discontinuity. So now let's look at how we evaluate the intervals of continuity for some functions. Okay? Okay, so of course, if you have one function, then it's easy to check, right? But when you have piecewise defined function, that means the function defined over different intervals. Okay, then the process becomes a little bit more tedious. Okay, so let me guide you through the logical sequence. So in order to evaluate the interval where the function is continuous, what one can do is to look for the discontinuous points first, and then just exclude them if necessary. Keyword is if necessary. Okay, I'm going to demonstrate why if necessary. Now, for example, if you consider this piecewise function, now look at the first function. Now I'm going to look for discontinuity in 1 over x. Okay, I know that in 1 over x, there is a discontinuity at x equals to 0, infinite discontinuity, right? X equals to 0 because 1 over 0 undefined. Okay, but x equals to 0 is not inside the interval. It's not inside x equals to, it's not inside x less than minus 1. Where is x less than minus 1? You look at the graph. X less than minus 1 is on the left, to the left of this vertical line here. So this part, your 1 over x is entirely continuous. You see? Continuous. So the discontinuity here at x equals to 0 is not part of the function defined in its own interval. So therefore you have to ignore. Don't consider x equals to minus 1, don't consider x equals to 0 as a discontinuity in this function, because this function is not defined of 1 over x at x equals to 0. Understand? So this is not a discontinuity for f. Okay, so ignore it. Okay, okay, then after you check the first guy, right, then you have to check the second guy also. But you see the second guy, right, 3x minus 2 is what? It's polynomial. It's a first degree or degree 1 polynomial, which is also the straight line function, linear function. So this guy got no discontinuity itself because it's just a straight line. So no need to check. Then what about the third one? The third one got to check. So the third one is a rational function, and you can see that it's discontinuous at x equals to 3. This guy, okay? So discontinuous at x equals to 3. You see, right? But x equals to 3, is it inside the interval? Yes. 3 is more than 2. So it's inside the interval where the function is defined. So therefore, you have to consider this. X equals to 3 is indeed a discontinuity of function f. So later got to exclude when you define the continuity intervals. Okay? Yeah, so to be very detailed here, okay, why is it removable? Because you can check the limit, you can solve for the limit. If the limit exists, then it's removable. If the limit doesn't exist, then it's not removable. So we did a check here. Let's take the limit, x go to 3, then you notice that actually this is 0 over 0. Okay, then after that you do factorizing, something that we've done before. Then after that you cancel off, and then you realize that the limit is actually 5. So limit exists. So limit exists, therefore it's removable. Okay? So therefore, after you have checked for the discontinuities within each function, right, you're going to exclude them later on, you also have to evaluate the interval transition. Okay, so interval transition is what? When you have a function change to the other function. For example, at x equals to minus 1. Minus 1 is an interval transition. Okay? 2 is another interval transition. You see? So therefore, you just check whether the limit equals to the function value at x equals to minus 1 and 2. How? Check the left limit, see if it's equal to the right limit or not. Okay? So you see, left limit at x equals to minus 1. So on the left of minus 1, what is the left of minus 1? 1 over x. The function is 1 over x. You see? Left of minus 1 means less than minus 1. So therefore, use the function 1 over x. Sub in 1 over 1. 1 over minus 1. Minus 1 is the limit. Then I check on the right. So minus 1 plus. But what's the function? The function is the 3x minus 2 function. So we just sub in 3 times minus 1 minus 2. So it happens to be minus 5. Okay? So minus 1 not equals to minus 5 what? Can you see? So the graph here actually can see this is minus 1. But this one minus 5. So therefore, jump this continuity. Okay? Because left not equals to the right limit. So that's done. Then x equals to 2. Check the same thing also. 2 minus on the left. Then the function is this orange function, 3x minus 2. So you sub in 3 times 2, 6. 6 minus 2, 4. Okay, so just KIV 4. Then after that, 2 plus. Sub in. So 2 plus is here. Okay? Which is given by this expression. So therefore you sub in. Then you realize that also 4. Okay? So 4 equals to 4. So the limit exists. It's 4. And the limit is also equals to the function value. Right? Because what's f of 2? F of 2 at x equals to 2, you sub in. So therefore you also get 4. Because you did a direct substitution here. Okay? And therefore this number is the function value. So hence you notice that together, how many discontinuities have we found? We only found 2. One is at minus 1. The other is at 3. So altogether got 3. Got 2 of them. Minus 1 at 3. Minus 1 and 3. So therefore you can see that I just omit minus 1 and 3. Okay? So what's the continuity interval? Minus infinity to minus 1 before minus 1. Union. Minus 1 to 3 before 3. Union. 3 to infinity. Okay? So of course this is also in agreement with the graph here. Can Okay? So there's a discontinuity here. Right? And then at 3, there's also another discontinuity. So there's a hole here. Is that alright? Okay. Any questions? So therefore, the approach is that we need to check 2 things. One is within the functions themselves, in each function. And the other one is inside the, or rather at the interval transition. Okay? So of course, first time you see this, like, wow, very messy. So we're going to look at another example. Okay? So, step 1, check for discontinuities in each function, in their own interval. Step 1, So there's only 2 functions, And I can see that second function got no discontinuity, Because this one is what? Exponential function, continuous everywhere, Then it's only this division by 0, possible division by 0 at the denominator, right? Such that it can give me a discontinuity. So then I just let the denominator go to 0. Then I solve. You see? X squared plus 2x minus 3 equals to 0. Then I get factorize. Then I get x plus 3 times x minus 1. Then I notice that I have minus 3 and 1. Okay, but you have to be careful. As I mentioned, right, you have to check whether the point, the discontinuous point, is inside the interval or not. So minus 3 is inside this interval, x less than 0. But 1 is not. So therefore, reject x equals to 1. It means there is indeed a discontinuity at minus 3. Then as I mentioned, the second function, 3e to the power of x, no discontinuity. That one just let it be. So no more function to check already. So I check for the transition interval. Then apparently I only have one transition interval because there's only 2 functions. So therefore transition interval is 0. So I just check what is the left limit and the right limit at x equals to 0. You see, left limit. So left limit, I must use the first function. Okay? So therefore, left limit, I just do direct substitution. 0 minus 9 over 0 plus 0 minus 3. So the answer is minus 9 over minus 3, so the answer is 3. So the limit is 3 from the left. So now you need to check the limit on the right, see if they are equal. So I also sub in 3e to the x, right? So I also sub in x equals to 0 to 3ex. So direct substitution first, 3e to the power of 0. Then it's just 3 times 1, 3. And because 3ex is defined at x equals to 0, so it's also f of 0. Then the result is clear because 3 equals to 3, what? That means the left limit equal to the right limit, then equal to the function value. So hence we can conclude that the function is continuous at x equals to 0. Which means in totality, there's only one discontinuity at minus 3. So you just exclude that point can already. Any questions? So hopefully with the second example is clearer on the procedure, just two-step procedure. Yeah, so actually I also plotted the function in decimals just to show you that indeed our result is the same, is correct. Okay, so this is the first function for x less than 0. You can plot in decimals. Okay, so the red curve is actually the first function. And then the blue curve 3e to the x is for x more than or equals to 0. It's the blue curve here. So you can look at the function and it actually is continuous indeed at x equals to 0. That's what we found lah. Okay, it's continuous. But however, at minus 3 there's actually a hole there. Decimals will not be able to show that hole. But if you move your cursor, your mouse cursor there, right, it will show that the function is not defined. Okay, because the hole is actually like infinitesimally small ma. It's only at just one point. Okay, so decimals will not show that. So hence you can see the graph in agreement with our findings. Okay. Okay, then I'm going to leave IVT for intermediate value theorem for next week. Okay, because this is making use of the concept in continuity. So maybe we leave it to next week for better, hopefully, absorption of this concept. So now we're going to start on with the tutorial questions. Wait a minute, I'm not looking at the correct thing. Where's my tutorial? Okay, so question 1 is just trying to assess your understanding of the limit operator from graph itself, from a graph itself. Okay, so I don't give you the function, I just show you the graph of the function. Then you're supposed to identify what are the limits given here. Okay, so I, under the request of the students just now, I went through the first 3. So I'm not going to go through the last 4. Okay, unless you have an issue with those. Can you see the first one? The limit as x goes to minus 2 plus. So you can see minus 2 plus is minus 2 but on the right of minus 2 ma. Plus means on the right lah. So you can see the limit is what? Approaching 4. The function is approaching 4. Okay, so the answer is 4. Then the second one, the limit of f as x approaches minus 1. Then you can see from here, minus 1, the limit is 1. Trying to go to 1 for f. So therefore this is 1, the second one. Then they ask you for the third one, right? What is the limit as x approaches minus 1? That means you have to consider from left and right to answer whether this limit exists or not. Then from the left, we already found that it's minus 1 already. From the left, right, is 1. You see here? Then on the right, so you can see from the right, is minus 2. You see? On the right, the limit is minus 2. So therefore, the left limit not equals to the right limit. So hence, this limit doesn't exist. Because 1 not equals to minus 2. Is that okay? So any problems with the understanding of getting the limit from a graph or not? Okay, right. This is like probably one of the easier kind of questions on limits. Just visually inspect can really. Okay? So if no, then I'll leave you to try and get the solutions for the last 4 limits. Okay, question 2. So question 2, this one, yeah, I have to go through in the earlier class. Okay, so this is like testing you on, can you show that 0 to the power of 0 is actually an indeterminate form? Because I think in the lesson, in the lecture, right, yesterday, we showed like 0 over 0, then infinity over infinity. Then we also showed that 1, why is it that 1 to the power of, why is it that 1 to the power of 0 is an indeterminate form, right? 1 to the power of 0. Okay, then why is it that like 0 to the power of infinity is an indeterminate form? That kind of thing. So therefore 0 to the power of 0 we didn't address. Okay, so let's look at it now. So the approach is similar to what we covered in the lecture, in the sense that, right, you really just have to consider the different so-called speeds that the base and the power approach 0. Because f and g, they are trying to approach 0, as can be seen from here. Okay, but f can approach faster or g can approach faster. Okay, so case 1, right, let's say if the base f approach 0 faster than the power g, the exponent g. Okay, so that means f is close to 0 already, very close to 0. But g is not that close to 0. So that means there is still like 1 over 10 million, that kind of thing. A very small number, okay? But if you consider what's the value you can get from this, right, it's actually 0 to the power of some root, right? Like a million root, kind of. But 0 to the power of anything that is non-zero is 0. It's just a root function, okay? Like 0 to the power of half, 0. 0 to the power of 1 quarter, 0. 0 to the power of 1 over 10 million, 0. That's case 1. Then case 2 is, right, the base f now approach 0 slower than g. So what's going to happen? You just swap. So this is 0.00001 to the power of 0. That means the exponent g already very close to 0 already. So therefore, what's the value here? The value here is 1, because any non-zero number to the power of 0 is 1. So therefore, you see, dependent on what is your function f and g, in the sense that if the functions are different, right, they can approach 0 with different speeds. Okay? So therefore, different speeds can give you different limits. So if that is the case, that means 0 to the power of 0 is indeterminate, which means that we need more methods or more steps to evaluate this limit. Is that all right? Can okay? So therefore, we have showed that this is indeterminate. Any questions? Okay, good. So let's look at question 3, which I also went through. So you're supposed to determine the horizontal asymptotes, okay, of the two expressions here. I mean, as in f of x, right, that is piecewise defined. Okay, then how to get the horizontal asymptote? So this one we covered in, I think, topic 1 as well as topic 2. Okay, that is right. The horizontal asymptote is the limit of the function as your x approach plus and minus infinity. So as you let the function, or if you let x go to positive infinity, then you see whether the function value will go towards some horizontal line or not. So this is something that we have been always seeing with rational functions. So let's say x 1 over x minus 4. Okay? So you can see that if I zoom out, right, I can see that x equals to, y equals to 0 will be a horizontal asymptote. The x-axis, you see, because the function value, right, you can see the function value approach 0 as your x goes big. As your x approach infinity, right, your function value is going to approach that asymptote. Okay? So therefore, y equals to 0 will be the asymptote. Okay? For this function. So how you evaluate that? Is simply to let your x go very big and very small. Okay? So therefore, plus minus infinity in that sense. Okay? Yeah, so therefore, you need to evaluate the limit for the first and second functions accordingly. So the first function, because it is only defined for negative x, so therefore you have to let x go to minus infinity. Okay? You see this one, minus negative. So just let x go to minus infinity. Okay, now we demonstrate the usage of the table. So first of all, we always try direct sub. But you see what happens when you do direct sub. You are having 1 minus, then this is minus infinity square is just infinity. So the 1, of course, wouldn't matter when your infinity is big. So therefore, this numerator reduces to minus infinity. Then when you have this minus infinity, you sub inside the x square, which is dominant. Then this x square becomes infinity. So hence you have this indeterminate form. So direct sub you try already because you always try that first. Okay? Try already, cannot work, indeterminate. So then what you do? You check. Factoring and divide off. This is only for rational functions giving the form of 0 over 0. What? You got this infinity over infinity, it's not the same form. What? So don't try. Don't do factoring and dividing off. Cannot work. Then compare growth rates. This one is when you have different elementary functions. Like for example, exponential divided by power function or power function divided by ln function, that kind of thing. Okay? So, but this one is what? This one is quadratic divided by quadratic. So that means the growth rate is actually the same. So you cannot compare growth rates also. Because the growth rate is the same. So therefore the second cannot work also. So don't use the second one. Then we look at the third one. Divide by x to the largest power. You look at this one. Oh, rational functions giving the indeterminate form, infinity over infinity. Correct? Is this type? So then I just try this one because this is the recommendation table. So which is what I did. You see? So I just divide by x squared, which is the largest power. At the numerator and denominator, simplify, I get minus. So if I found the limit right, and it exists, so therefore y equals to minus 4 is a horizontal asymptote. Okay? Any questions with using the table? Can, right? I think quite systematic. Okay? Yeah, then that's for the first part, the first function. Then you just repeat the same for the second function. Okay? Repeat for the second function. But the second function is only defined for 0 and positive values of x. So you should let x approach positive infinity. Okay? Can, so this part you DIY. I don't want to repeat the same story. So hence, by right, you should get x equals to 1/5. Y equals to 1/5 for the second asymptote. So there are two asymptotes in this function. Okay? So the second part you DIY, because I already demonstrated for the first part already. Any questions? Good. So next up, 4H. Okay, so question 4 is a bunch of limit evaluation problems. Okay, so under the request of the earlier class, I went through H and K. I think some of them tried. So let's look at H. It is H. Okay, so H is quite similar to the lecture example in the sense that, you see, I always try direct sub first one. Okay, so direct sub in x equals to minus 1, I'm going to get 0 over 0. So indeterminate form. Okay, then I go back, look at my table. So I shouldn't use dividing by x to the largest power because 0 over 0, not this type. What? You see? Cannot. So therefore, factoring and dividing off cannot factor already. Look at the expression, how to factorize. This one still can factorize. Cannot factorize. So which means that the first one cannot, this second one cannot work. Compare growth rates also cannot work because they are both root functions. Then this one cannot work also. Then become the fourth one already. So rationalizing. Functions with root expressions. So this one conform to our problem here already. Okay? So therefore I try the rationalizing approach. And then because the earlier class requested me to rationalize one by one. Okay, because in the lecture, right, I rationalized both at one go. Okay, but you can always do one by one. So for example, right, I try to rationalize this first. You see? I just multiply by the conjugate. Then after I multiply, I get root expression removed, so I get x plus 2. Then minus 1 times 1 is minus 1. Then the whole result is just x plus 1. Okay? Then once I get to this point, right, then the denominator cannot simplify further. So then what one can try is just to sub in. Because this one you simplify already. So therefore you sub in. Okay? Direct sub again. So direct sub, you realize that, you got 0 over 0 again. So cannot work. So then what you do? Rationalize again now, because you still have this root expression here. Okay? You rationalize this, but you never rationalize this one. So therefore, that's what we did. Continue to rationalize the second root expression. Okay? So you see that after you multiply out, right, you get this x plus 1 here. Then the denominator is 4x plus 4, or 4 plus 4x. Because from here you can see, after you multiply, 3 times 3 is 9. Then minus of 5 minus 4x. So 9 minus 5 is just 4. Then minus 4x is plus 4x. So what you need to do is to recognize that 4 plus 4x and x plus 1 is just different by a factor of 4. So I factorize out the 4. So become 1 plus x. 1 plus x can cancel with x plus 1, the same thing. Like that, right? You notice what happened? You are actually cancelling the 0 over 0 problem. Because when x equals to minus 1, this is 0, then this is also 0. So this is the secret of rationalizing. Because it allows you to cancel off, right, the 0 over 0 term. Okay, so much so that you're only left with this expression. So therefore the answer is what? 1/4 times sub in. So you get root 3 plus root 9, this guy, and then over root 1 plus 1. So that will give you your limit of 3/4. This one is the green part. Then this one is the blue part. Okay? For the individual root expressions. Okay, good. So next up, they requested also me to go through 4k. Because 4k is kind of weird. Because it's not a rational function. But it does have a root expression. So as usual, direct sub first. So if you do direct sub, right, you notice that this is infinity. I mean, x approaches infinity. So if I sub in, I get infinity square, which is just infinity, plus 10. Then this is minus infinity. But infinity plus 10, you take root, also infinity, right? So it's infinity minus infinity, then it's indeterminate. Because you don't know whether the two infinities are equal or not. That means, are they of the same kind of magnitude? Or is it the first one is bigger than the second one, or the second one bigger than the first one? You don't know which one is which. So therefore, since it contains root expression, right, what do you do? Rationalize. Because that's the only trick we know, right? Okay, for root expression. So therefore, you can see that I just rationalize by multiplying by the conjugate. Okay, then this part I can simplify, remove the root. Then I notice that, this one, x squared minus x squared, so I left with 10. So it's really 10 divided by this. Then nothing else to do already, so I just try substituting in again. So indeed, this is 10 over infinity plus infinity. Then 10 over infinity is confirmed 0. No questions about that. So that's it. That's the limit. It's not an indeterminate form. 0 is the limit. Okay, and why is 0 expected? If you look at this expression, some of you may think that, it looks like 0. Why? Because when x is big, this x squared is dominant, right? So the plus 10 you can just throw away. So you're left with x squared when x is big. Then root of x squared is x what? So this is of degree x. This looks like x when x is big. Then x minus x obviously is 0. You understand? Okay? So maybe I give you another example. What if this one I change to cube? What do you think the answer will be, right, if I change this to cube? That means the 2 will become 3. That means without doing anything. Without doing anything, right, what do you think the limit is? Same. Why same? That means this is cube of x, not square of x. Any guesses? Same is incorrect. If I change this to cube, what do you think the limit is going to be? I mean, I can of course work out the same thing. I can get the answer. But let's say by just like comparing the order of magnitudes of the first term and the second term, you can actually have a feel of the answer. You see, root of x cubed, correct or not? So when x is big, the plus 10 is useless. So this thing behaves like x to the power of 3 over 2 minus x. So therefore, if you sub in infinity, this infinity is bigger Because the power is more than 1, what? This one is just x to the power of 1. So which means this is going to approach a bigger infinity for the first term minus a smaller infinity for the second term. So therefore the answer is infinity. Okay? You can actually do the rationalizing and work this out. Okay? So just giving you like a different perspective, indeterminate form. Because that will give you 1 to the power of, ln 1 is 0. 1 to the power of 0 is indeterminate. So how? And 1 to the power of 0, you look at the table, got no such thing. Correct what? Got no such thing. 1 to the power of 0 is not 1. Why is not? This is indeterminate form. Maybe we didn't address this. Okay, let's look at the lecture notes again. Okay, look at the indeterminate forms. Where is it? Hold on. There's no 1. 1 to the power of 0 is 1. Okay, the answer is 1. I've mistaken that this is indeterminate. So this is indeed 1. Sorry? E to the power of 0 is also 1. Infinity to the power of 0 is indeterminate. Okay. Yeah, so I didn't remember the correct thing. Okay? 1 to the power of infinity is actually indeterminate. Right? So maybe I messed it up. So 1 to the power of 0 is a direct 1. That's correct. Okay? So what about the rest? The rest okay, You try, What about J? This J. So interestingly, if you have direct substitution, you notice that this guy is going to be what? Minus infinity to the cube, right? So it's still minus infinity, Because minus infinity cube, negative number cube, you still get minus infinity, Then this e to the minus infinity. So therefore this is e to the infinity, what? So therefore, this is minus infinity times infinity. Because infinity, e to the infinity is still infinity, right? So the answer is minus infinity. Is that right? Which part not clear? Is that okay? E to the infinity is an e to the very big number, a base to a very big number. So therefore, you still get a very big number. In fact, e to the infinity is even bigger than this infinity. Because exponential grow very fast. Exponential function grow very fast. So this infinity is really big. So any other questions you want me to go through? Which one? Question 5 squeeze theorem I didn't go through. So this one you just try. Okay? Because similar to what the lecture examples have gone through. Question 6 I did went through B. Because B is not easy. Does not lend itself to evaluating directly for the discontinuity. So we know that there's a discontinuity possibly at x equals to 2, right? Because there's a denominator here. But how to evaluate the type? How to evaluate the type? So which means in order to evaluate the type, you have to evaluate the function from the left as well as from the right of 2. Okay? So therefore, you need to rewrite this modulus function into a piecewise manner. Okay, so let me go through this step by step. Because this one, you need to be familiar with it. Because we're going to keep using this concept throughout Math 2 and 3 as well. Math 1, 2, 3. Okay, so the story is like that. You see this modulus expression is trying to modulus this x minus 2. So you just have to consider 2 cases. One is when x minus 2 is positive. So when x minus 2 is positive, the modulus sign, this modulus sign is not doing anything. Because the modulus is trying to turn whatever this expression is, right, into the positive version. That's what the modulus is trying to do. But if the argument here, if the thing here is already positive, then the modulus is just a bracket. Because the result is the same, what? It's like you modulus 3. Then the answer is 3, what? So therefore, change the modulus to bracket. So once you change the modulus to bracket, you can observe that x minus 2 can divide away with the x minus 2 at the denominator. So the answer is really just 4. That's what the modulus is trying to do. So therefore, you just multiply the negative term by a negative 1. You see? Okay? So this itself is negative. So minus times minus become plus. So then when you have that, right, you simplify. Cancel off the x minus 2, you get minus 4. So what is the simplified function? This. 4 and minus 4 over 2 different intervals. So once you write this, then you can evaluate this continuity already. So as usual, in each function, you ask, are there any discontinuities in each function? The answer is no, because these are constants. Okay, they are just horizontal lines. So it's continuous. Then however, you also need to check at the interval transition. I mentioned that before. So at x equals to 2, 4 not equals to minus 4 what? No, the answer is basically just jump this continuity at x equals to minus 2 because the question here asks for, right, determine any discontinuity and its type. So you need to know where is the discontinuity and what type it is. So therefore, after evaluating the function, we realize that actually there's a jump discontinuity at x equals to 2. Yes. Because it requires us to state the type in the question. If the question never say type, just say determine the discontinuities of each function below. Then you no need to evaluate the type. For example, like let's say this expression. Let's say you no need to evaluate the type. Then it's very clear that the x equals to 9 is a discontinuity. Then just that's it. Just 9 minus x equals to 0, x equals to 9. Discontinuity at x equals to 9, finish. So how to evaluate the type? You have to see whether the limit exists or not. If the limit exists, then it's removable. If the limit don't exist, left limit not equals to right limit, then you get the step. So that's why I show you the 3 types here. Okay. Left not equals to right is jump. Then if you have infinities, then it's infinite. This one very clear. Then if the limit exists, it will be removable. Okay? Yeah, and then okay, so I think A and C you do A and C should be more straightforward. So besides that, I also did. Okay, question 7 is the evaluating the interval where the function is continuous. So it's very similar to our lecture examples. Okay, so I think this one you DIY first. Then 8 also DIY. So then I'm going to finish the class with question 9. Okay, so question 7, 8, 9, similar type of question. Okay, but 9 in the 9 is in the sense that, right, you have this A and B variables, okay, or constants that you are supposed to determine the value for in order to make the function entirely continuous in the whole domain. Okay, so which implies that you have to make sure that the limit equals to the function value. So this is the approach. So first of all, you notice that ax plus b and 2ax minus b, the first and third functions, they are continuous in their own intervals. Okay? So no problem with that. So which means you only need to check at the interval transition. Then you notice, right, on the left of 1 is one function, on the right of 1 is another function, then exactly equals to 1 is a function value. So which means that x equals to 1, there's a function transition. So therefore, you really just check whether the limit at x equals to 1, right? Or rather, you want the limit at x equals to 1 to exist and also equals to the function value. So this has to be fulfilled for continuity. You see? Left limit equals to right limit. That means the limit exists already. Then that limit must be equivalent to the function value. So that's the definition of continuity. So then we just do left limit. Limit of left of 1. You have to use the ax plus b function. So ax plus b, x equals to 1. So equals to a plus b. A plus b must be what? Must be 4. Because you need it to be f of 1, which is 4. Then same thing. On the right of 1, 1 plus. So 1 plus, you have to use this because it's more than 1. So then you have 2ax minus b, sub in x equals to 1. So you get 2a minus b. So 2a minus b must also be equivalent to 4, the f of 1. So now you got 2 equations, 2 unknowns to solve. So proceed to solve them in whichever way you prefer. So I use the elimination method here. Okay? So you're going to get a over 3 and 4 over 3 for your a and b respectively. Any objections? Okay? So maybe you can demonstrate using the graph. Okay, so let's see. So I should go through this with you. Okay, so you can see the first function, right, is ax plus b, correct or not? So ax plus b, you define the interval. So the interval is x less than 1 ma. Okay, interval have to put inside the curly brackets. Okay, so we're going to add a slider for a and b here. Okay, so let me show you the graph. You see, Okay, so what is the second function? The second function is 2ax minus b. So therefore, let's input 2ax minus b. Then what's the interval? X more than 1. So obviously, you can observe that if your a and b are 1, then there's a discontinuity. Then function value at 1, right, is actually 4. So you want the two lines to converge to this point 4 at x equals to 1. Understand the logic, right? And 4 over 3 respectively. Then you can get the convergence to the point 4 at x equals to 1. So this verifies our solution. Because if you don't get these two values for a and b, right, this thing will be discontinuous. Like for example, if I change this to 2, then it cannot really what? You see? If I mess around with this, you see? So it's only at exactly 8 over 3. Then I can get a nice perfect fit. Any questions? So you can use the graph plotter Desmos, right, to inspect your solution as well. Okay? Yeah, so we are done for today because the rest of the questions deals with the intermediate value theorem. So we'll cover that next week before your quiz 1. Okay, so the quiz 1, I've mentioned that it will be on topic 1 and then it will be on the second hour of the lecture next Thursday. So first hour we still go through, finish up our topic 2 as well as the tutorial questions. Then after that we will just conduct the quiz. If you finish early, you can go. Okay, remember to bring your laptop or tablet to do the quiz with internet access. Okay, and then regarding your cheat sheet, maximum 4 pages of A4 paper. Maximum 4 pieces of A4 paper, so 8 pages altogether. Maximum. You prepare your own cheat sheet. Is that right? Okay? Yeah, so the same cheat sheet. I mean, you can of course modify but then you're still going to use the cheat sheet for your midterms. Same. Sorry? Yes, you can print. So you can do like very small. Then you zoom until very small, a lot of small formulas. It's up to you. Okay? So one question on the movie AlphaGo. I hope you have watched it already. If not, just watch it over the weekend. Okay? Next Monday, I'll upload the solutions for you to check. But you do first. Don't look at the solution and then think that, oh, I understand the solution. You understand the solution is not the same as when you do it yourself. Very different.